Hi, welcome to video 3.1b, the extreme value theorem. Okay, so the extreme value theorem, I'm going to call it the EVT, says that if you have a function continuous on a closed interval, so both sides square brackets, then, that's the only condition, then f has both an absolute minimum and an absolute maximum on that interval. If you look at this graphically, in each case you're starting at a filled in dot and stopping at a filled in dot, as you can see here and here, okay? And your function is continuous the whole time. So what's going to happen is somewhere on that graph, unless you drew a horizontal line, somewhere on that graph you're going to have a highest point and a lowest point, so an absolute max and an absolute min. Now in this particular case, they happen to both occur at the endpoints of the interval. In this particular case, they happen to occur at critical numbers between the endpoints of the intervals. And here you have one of each. You have an absolute max at a critical number, and you have an absolute min at one of the endpoints. So you are going to have to justify that the extreme value theorem holds, which means you are going to have to establish that the function they've given you is continuous on the closed interval they've given you. You're going to do that like we did before by stating the type of function it is. All of these functions are continuous on their domain, which is, state the domain, and therefore continuous on there. Once you know that the extreme value theorem holds, and you do know there is an absolute max and an absolute min on the interval, the question is then to find them. Well, we know they're going to occur either at endpoints and or at critical numbers on the interval. So you'll need to find the critical numbers. Remember, you need the domain of the function. You'll find the derivative. What values of x in the domain make the derivative 0 or undefined. Once you have those critical numbers to find the values of the absolute extrema, you're going to find f of a, the left endpoint of your closed interval, given closed interval, f of b, and f of each critical number that you found that's between a and b. Once you have these y values, the largest of them is the absolute max value, the smallest is the absolute min value. Okay, in 17 through 36, if we look at 17 through 36, it says locate the absolute extrema of the function on the closed interval. So you'll notice in every single case here, the interval they're giving you is a closed interval. So, for example, number 22, here's the function, here's the interval. Does the extreme value theorem hold? In other words, is that function continuous on that interval? In this case, of course it is, because it's a polynomial function continuous everywhere. Now we need to find the critical numbers. We know they occur at either the endpoints or the critical numbers, so we need the critical numbers. The domain of our function is all real numbers. Here's the original function. Here's the derivative. It never doesn't exist, but it does equal 0 at x equals plus or minus 2. So the three numbers we have to try are the endpoints of the given interval and the only critical number that we can try, which is the one that's between 0 and 4. Remember, the only critical numbers we're looking at are the ones on the interval from 0 to 4. So we try f of 2. The largest of those is 16. The smallest is negative 16. So the absolute maximum value is 16. The absolute minimum value is negative 16. They could ask you for the points, the absolute maximum point and absolute minimum point. That would require you to write the x-coordinate and the y-coordinate. Okay? All right. Numbers 37 through 40. Locate the absolute extrema of the function, if any exist, over each interval. You'll notice only part A is a closed interval. After that, it's either half open or totally open. So the extreme value theorem will only work with a totally closed interval as long as your function is continuous on that closed interval. The others, who knows, might not. They might have both extrema, absolute extrema. They might only have one and not the other, but they might have neither. You're going to need to graph these in order to make that determination. So 38, function is y equals 5 minus x, and the interval they're giving you is the interval from 1 to 4. So obviously that's just a line with a slope of negative 1. So I plot the point 1 comma and 4 comma. Plug that into here. I find out that's the point 1, 4. That's the point 4, 1. Obviously, by pure observation, you just graph it and observe. The highest point is that 0.14, so the absolute maximum value is 4, the absolute maximum point is 14, and here's the absolute minimum point and value. Part B, on the other hand, is half open interval. So it is closed at 1, which means there's a filled in dot, but at 4 there's an empty dot. So there is a highest point, an absolute max point, but there is no absolute minimum point or value. In number 40, same question, only this one is, these are two lines. This is a parabola. This is a little bit more complicated. It's what we call a semiconic. You learned that in Algebra 2 and certainly in pre-calc. If you square both sides of that expression, you will end up with x squared plus y squared equals 4. Now normally that's this entire circle. However, the original function was y equals positive the square root of, so it's only half of that circle. It is the top half because the y's are positive. So here's your graph. So if they talk about the closed interval from -2 to 2, you have an absolute maximum value of 2, an absolute minimum value of 0. But of course, you have two absolute minimum points. If, on the other hand, you look at part D, which is the half open interval 1 to 2, there's a filled in dot at 1. You can plug 1 into the function and see that that's root 3. And when you plug 2 into the function, you have your 2, 0, but that's an empty dot. So there is an absolute maximum value of 3, but there is no absolute minimum value. In 41 through 46, they say use a graphing utility to graph the function and then locate the absolute extrema of the function on the given interval. So they do give you a function. In number 42, it happens to be a piece function. We've talked about how to enter that. And they do want it on the closed interval from 1 to 5. That's going to be your window, your x-min, and your x-max. So here's what you get when you graph that function on that interval. You'll notice the highest point is the one at the far left, and the lowest point is the one at the far right. So obviously the maximum value is going to be your f of 1, whatever that is, and your minimum value will be f of 5. So now, since that's stored in F1, you'll just go back to the calculate screen and do F1 of 1 and F1 of 5. That's the fastest way to do it. Of course, if you're in Scratchpad, this will not work. Okay, in 57 through 60, all right here, it says determine from the graph whether the function has a minimum in the open interval from A to B. Okay, does it have a minimum point? So again, it's going to depend on the graph itself and the filled in or empty dots. So if we look at 58A, the lowest point on the graph would have been this one, but there's no point there. Here, the lowest point is there, so yes, it has a relative minimum, and that also is an absolute minimum. Okay. And that's the end of video 3.1b.